If we have more than one variables, we call it multivariable, we can still have the error propagation, and we can present this using the Taylor series. And let's say we have two independent variables, u and v, and let's write the Taylor series for this example for the two independent variables. In this scenario, for u and v, let's say f u I plus 1 v I plus 1 is equivalent to. Now we try to predict I plus 1s with the current or I values of u and v plus. So we will have the derivative, but in this case, because we have two independent variables, we will have partial derivatives. For example, df divided by du, which is the derivative in terms of u, and ui plus 1 minus ui is the step size, and also the same thing for the derivative in terms of v, and this time vi plus 1 minus vi, like this. So this is the first order, and let's continue with the second order term. For that we have two factorials, and inside this we will have the second order derivatives and partial derivatives of the function, first in terms of u, and also the square of the step size for u, ui plus 1 minus ui square, plus 2. Here we will have a 2 term here, because not only the derivatives in terms of u and v, but also in terms of both u and v we will use, as you can see here, because it's a second order term, and the step size ui and vi also exists for the step size in this case, and this will continue with the plus del square f divided by del v square, because this was the remaining one, and this is because of v, we will use only v step size, vi minus 1 minus vi and square, and this goes like this. And the third term, it will be like 3 factorial and onwards. So what we want to do is we want to truncate from where? From the first order, truncate here, and write down the truncated terms. You can see here, that's just this term, and this term. We will write them down as the delta f. So when we make this truncation like this, delta f u and v as the prediction is equivalent to delta f divided by del u, delta u, these are the step sizes, delta values, plus del f divided by del v in absolute, del v step size. So the first term, this one, is this one actually, and the second term is this one. So the remaining is this. Actually, we moved this to the left side, and it became fi plus 1s minus fi's, which gives us delta f. So you need to remember that the subtraction of this is this. And all the partial derivatives here are calculated at base point I. Let's write that too. All the partial derivatives are calculated at base point I. So basically here and here, because we didn't write any I or I plus 1, you may be confused, and they are actually at the ith values, only at I, not I plus 1. So this is for the two variables, and we can generalize this for more than two variables, meaning n variables. Then for n variables, we can just extend this. Let's say we have x1 tilde, x2 tilde, xn tilde. And these are having errors delta x1, delta x2, delta x3, and onwards until delta xn, like this. And the Tyler series for this is now delta f x1, x2, and onwards up to xn, infinite terms, or finite with n. These are basically delta f, the partial derivative in terms of x1 times delta x1 plus partial derivative in terms of x2 and delta x2, and it goes this way until the end, which is the end term, delta f in terms of xn and delta xn tilde. So this is basically the general formulation for n variables to propagate the errors in variables during the operations. Let's have an example about this in the next slide. In this example, we will have a deflection problem of a sailboat mast, and we can calculate the deflection using this exact formulation actually. And we know that there are predictions of FL, E, and I, as you can see here, and there are errors of these in the measurements. Let's say we measured these or determine these with these kind of errors. And the question asks us to find the error of the Y based on this data. And simply, we can actually predict the Y value by substituting these into this exact formulation. Let's write it down to the left side. For example, I can simply write it down here. Y tilde, the prediction, is simply f prediction, L prediction to the power 4 divided by 8, E prediction, and I prediction. So we can simply write these values over here into this equation and find a value of 0.16, 40, 25, which is mirror, which is the predicted displacement. So let's keep this in mind, and we want to also find the propagated error. Well, you may think that maybe you can just write these over here and find an error value, but it doesn't work like that. We actually use the Tyler series, and let's use the Tyler series prediction. If you remember from the previous slide, the error propagation of the function output, which is y here, and we call it delta y, is in terms of the inputs. We have 4 inputs, F, L, E, and I, and we basically use the partial derivatives in terms of the terms. So here the first term or first variable delta f, of course these are the predictions, and delta f, the step size or the error. Actually, this step size becomes the error now for this error propagation of using the Tyler series. The second term is the partial derivative in terms of the second input, which is L, and delta L, plus the partial derivative in terms of E and delta E, plus finally the partial derivative in terms of I and delta I. So we have all of these values, But before writing the values down, we need to calculate the partial derivatives using this formulation. So for the first term, we will have the derivative in terms of f. So we will have this f here becomes 1 when we take the derivative. So this becomes simply L4. The remaining terms can be written because these are assumed constant. Not the only variable is now f here in the partial derivative. Plus in the second one, L, we will take the derivative in terms of L. So the function becomes 4fL cube because L was to the power 4 and 8ei and delta L, plus here in terms of E, the partial derivative becomes FL4 divided by 8 E square I delta L, plus here FL4 divided by 8 E I square, this time because it is partial derivative in terms of I, and delta I. So here we simply know that these are also the predictions. Let's don't forget the tilde values. Here as well, here too, and here too. Now if we write everything down here, so these values are for the predictions over here, here, and these values are the errors here, 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 and here. When we write them down, we simply find the delta y value as 0.011482, which is just tilde. And this is also meter. So these results show that we have a prediction of 0.16 with a propagated error of 0.01. You can see here. So this is just the prediction. This is the error in the prediction. And it is estimated by the Tyler series. And if we write these down together, we will find the prediction is made y tilde plus minus delta y, like this. And it is 0.16 4025 plus minus 0.011482 meter, which shows that the error is in between plus minus 0.01 of the predicted value. So if we just subtract the error, for example, y min becomes, y min is equivalent to 0.152543, and y max is just the summation of the prediction value with the error or propagated error. It's 0.175507 meter. This is meter 2. So we actually found the error, the propagated error, with an estimation of Tyler series. We do this when we don't know the exact value of the error propagation actually. But here we also have the exact formulation. Then we can also calculate using this the exact propagated errors with the minimum values, also with the maximum values. What I mean is that we have the f value, for example, which is changing between plus minus 30 Newton meter. So we can subtract this error from this to get the f min. Also we can have f max by summing them, and we do the same for these and get minimum and maximum values. Then we put them into here to get an exact y min and y max values. So let's write down the minimum and maximum values first. Here, for example, f min is simply 750 minus 30 is 720, and f max is simply 750 plus 30, which is 780. We do the same for all of these. Lmin, and let me write just the results. It's just 8.97, and Lmax is 9.03, and Emin is 7.45, 10 to the power 9, and Emax is 7.55 times 10 to the power 9, and I, if we subtract and add the error, 0.000495, and I mean, by the way, and Imax is 0.000505. Let's use them to get the exact y mean and exact y max, and we can calculate them below over here. Exact y mean is equivalent to simply f max for the minimum value. We will get the min values here. F min and L min to the power 4 divided by, so at the denominator at the bottom, because we will make this minimum, we will use maximum values, Emax and Imax, so that we can have the minimum y value. So these are 720 times L min is 8.97. We calculated them at the top right side. 8 Emax is 755 times 10 to the power 9, and Imax is 0.000545, and the result from here is 0.1528.118. We can also calculate the exact y max, which is f max L max to the power 4. Of course, these are the predictions anyway, because the question gave us the prediction values, divided by 8. This time E min, because if we divide by minimum values, we get a maximum value, and I min. And if we write these down, it's 780 for f max. L max is 903, divided by 8 times E min is 7.45 times 10 to the power 9, and I min is 0.000495, and the result from here is 0.17590. And we can calculate these minimum and maximum values calculated exactly by the predicted values. Check these out. You can see that, so we will compare this with this and this with this one, because these are the max values. You can see we have pretty close results. It's about 0.15, this is about 0.15, and this is about 0.175, and this is also about 0.175. So the errors are close enough. We can say the predictions of errors, predictions of propagated errors actually, are close enough. So this example shows us that the first order Taylor series is a good approximation of the propagated error when we compare with the exact values. In this slide, we will talk about the error bounds. And if you remember, in the previous slides, we showed that the error propagation for the multivariable functions can be found by the Taylor series in the first order. You can see here with the partial derivatives and multiplication by the delta or error values. And we can use this to define error propagation relationships for common mathematical operations. And in your book, you can see table 4.3, which shows, for example, for the addition, actually the error is just added, and it is basically the estimated error is just addition of each error. And the subtraction is minus, but the estimated error is also summation. It is important. For the multiplication of the errors, it is basically the predicted value times the error and predicted value times the error, but the errors are, for example, if we are using u for the predicted value, the error is v. Here, if we are using v, the error is u in terms of u. So we will make a summation of these to get the estimated error. For the division, we will also have a similar result like this, but divided by v square, the predicted v value square. So if we use these formulations, we can simply have a prediction of the error propagation for the common mathematical operations.